Hello and welcome to this lesson on sharding, definition and core principles. In today's data-driven world, managing ever-growing datasets and ensuring high performance for our applications is a constant challenge. As database administrators, back-end developers, or data engineers, you've likely encountered bottlenecks with single monolithic databases. Sharding is a powerful technique designed to overcome these limitations, enabling databases to scale horizontally and efficiently handle massive amounts of data and traffic. It's a fundamental concept for building robust, high-performance systems. By the end of this lesson, you will achieve several key learning objectives. First, you will be able to clearly define database sharding and articulate its primary purpose within a scalable architecture. Second, you'll gain a solid understanding of the core principles that govern how data is effectively distributed across multiple shards. Third, we'll explore and identify different strategies for implementing sharding, each with its own advantages, disadvantages, and specific use cases. And finally, you will recognize the critical importance of the shard key, the fundamental element that dictates data partitioning in achieving effective and balanced data distribution. Let's dive in and unlock the power of sharding. So, what exactly is sharding? At its core, sharding is a method for horizontal scaling. Instead of simply upgrading a single, more powerful server, a process known as vertical scaling, sharding involves intelligently distributing your data across multiple independent database instances, which we call shards. Think of it like taking a single massive library and splitting it into several smaller specialized branch libraries, each managing a specific collection of books. The primary purpose of sharding is to dramatically improve performance, enhance scalability, and ensure higher availability, especially when dealing with extremely large datasets or high transaction volumes. By spreading the database load across many servers, you effectively eliminate the single points of contention and bottlenecks that a monolithic server would inevitably encounter. This approach contrasts sharply with vertical scaling, which eventually hits physical and economic limits. Sharding, however, allows you to scale out almost indefinitely by adding more commodity hardware, making it a highly cost-effective solution for growth. Conceptually, each shard holds a distinct subset of your total data. Together, all these shards form your complete logical database. When a query comes in, the sharding system knows precisely which shard to direct it to, based on the specific data being requested. This intelligent data distribution and routing is absolutely key to its efficiency. At the heart of any sharding strategy is the shard key. This is perhaps the most crucial decision you'll make when implementing sharding, as it fundamentally dictates how your data will be organized. A shard key is essentially a column or a set of columns within your database table that the sharding system uses to determine which specific shard a particular piece of data should reside on. Think of it like a postal code for your data, directing it to its correct address, its specific database shard. Its importance cannot be overstated. The shard key is critical for both efficient data distribution across your entire sharded cluster and for ensuring that incoming queries are routed to the correct shard quickly. Without a well-chosen shard key, the significant benefits of sharding can be severely undermined. What makes a good shard key? Ideally, it should possess high cardinality, meaning it has a wide range of unique values to allow for many potential distribution points. It should also promote even distribution of data across all your shards, preventing any single shard from becoming an overloaded hotspot or bottleneck. And generally, it should be immutable, meaning its value doesn't change once assigned to avoid complex data migration issues. The impact of a poorly chosen shard key can be quite significant. It can lead to severely imbalanced loads where some shards are constantly overwhelmed with requests, while others are underutilized, creating those dreaded hotspots and severely impacting overall system performance and scalability. This is precisely why careful consideration and rigorous testing are absolutely essential when selecting your shard key. Once you've chosen your shard key, the next step is deciding on a sharding strategy for data placement. There are several common approaches, each with its own trade-offs. First, we have range-based sharding. Here, data is partitioned based on a range of shard key values. For example, all users with IDs from 1 to 1 million go to shard A, 1 million to 2 million go to shard B, and so on. This is simple to implement and efficient for range queries, but it can lead to uneven distribution if data growth isn't uniform across ranges, potentially creating hotspots. Next is hash-based sharding. With this method, a hash function is applied to the shard key, and the resulting hash value determines which shard the data belongs to. This approach generally provides a much more even distribution of data across shards, reducing the likelihood of hotspots. However, it can make range queries less efficient, as related data might be scattered across different shards. Then there's directory-based sharding. In this strategy, a separate lookup table, often called a directory or metadata service, stores the mapping between shard keys and their corresponding shards. When data needs to be accessed, the system first consults this directory to find the correct shard. This offers maximum flexibility, allowing for easy rebalancing and adding new shards, but it introduces an extra lookup step, and the directory itself becomes a critical component that needs high availability. And finally, for more complex requirements, hybrid approaches are common, combining elements of these strategies to leverage their strengths and mitigate their weaknesses. The choice heavily depends on your application's specific access patterns, data growth, and consistency needs. We've covered quite a bit in this lesson about sharding. Let's quickly review the key takeaways to solidify your understanding. First, we learned that sharding is a powerful and essential technique that enables horizontal scaling for your databases. This allows you to effectively manage vast amounts of data and handle high user loads by distributing data across multiple independent database instances, which we call shards. It's a fundamental concept for building robust, high-performance systems. Second, we emphasized that the shard key is absolutely crucial. It's the primary mechanism that determines where your data lives within the sharded system, and a thoughtful, well-analyzed selection of this key is paramount for achieving efficient data distribution, accurate query routing, and avoiding performance bottlenecks. Third, we explored the common sharding strategies: range-based, which is straightforward but can lead to uneven distribution; hash-based, which offers excellent data distribution but can complicate range queries; and directory-based, which provides maximum flexibility through a lookup service but introduces an additional lookup step. We also touched on how hybrid approaches are often utilized to combine the strength of these strategies. To conclude our lesson, here's a quick self-assessment question for you. Based on everything we've